Okay, so we are going to continue with matrices in Maxima, then R. So last time we did matrices, and now I'm going to combine matrices with lambda functions. So let me start with a simple lambda function. I am going to call it my fun, and lambda, I'm going to pass in x, and I am going to create x plus x squared. And let's define a matrix. And another matrix. So I am going to pass my fun of C. So that gives us x plus x squared. Keep in mind, in Maxima, when we do x squared, it would actually square each and every element and not do a matrix product. So if I passed my fun of C plus B, it will still treat C plus B as a single matrix, and it is going to pass it to the lambda function my fun, and it is going to return x plus x squared. We can multiply a matrix to itself by doing period, not asterisk, and we can square a matrix simply by doing double caret sign and 2. So both of those would give you the same answer because C times C is C squared. Let's take a symbolic matrix and let us define my fun of x. And that simply gives us x squared plus x because it treats x as simply a list element. So if we want a matrix with elements, then we'd have to define a matrix, a symbolic matrix. And 1 comma x, and pass my fun, or call my fun with the matrix x, in which case it is doing symbolic arithmetic and it's passing the matrix that we created, which doesn't have numbers, rather has symbols. So we can find the derivative, for instance, of this matrix, and you can see that it produces del x. By default, Maxima is going to try and do partial derivatives, and which is why we have del x. But if we don't want Maxima to do a partial derivative, you have to specify the variable that you're taking the derivative with respect to. And if we did that, the del of x is gone, and we simply get the derivative of the matrix x with respect to x. So there are plenty of utility functions in Maxima that we can make use of for basic linear algebra operations. So let me define a matrix A into 1 and 1 minus 1, 1. And that is a full matrix, and we can actually reduce it to a triangular form using the command triangularize. And what we have here is an upper triangular matrix. And we all know what an echelon form is. Let's take a matrix with completely independent rows and columns. And we can do an echelon form, and that is going to give us a triangular matrix again. So in this case, our echelon form doesn't have any row of zeros, indicating that the column vectors are all independent of each other. So let's take another case where we have a linear combination and let's do the echelon form of H. And that gives us a row of zeros as expected, because the third row is a linear combination of the first and the second. If I add the two rows, I would end up getting the third row. And of course, the rank of the matrix would be 2, because the number of linearly independent rows is 2. Going back to our lambda function, if we end up doing two matrices, we had X and G, and I'm going to pass them as separate elements of a list, and as you can see that the function operates on the first list, X produces that output, then it acts on the second element, which is G, and produces that output. So if you pass in a list of matrices, we're going to get a list of matrices back. If we don't want this behavior, rather we want to apply myFun to X and apply myFun to G separately, and perhaps do an operation in the middle, then we'd have to call myFun X plus myFun G. Strange. Let me try something else. Weird. Is a matrix. Interesting. I didn't expect to get this error. It's strange to me. It should work Perhaps there is an issue in the structure that we defined for the two matrices X and G. So typically we should be able to add two matrices as the outputs are matrices, but this seems to be quite strange. But let's move on. So I am going to define a new matrix. Let's say y comma 1 and 1 comma y, and let us define a new lambda function going to do t times t plus 2. And apply the function to a matrix. So we have x and we have y. So let's go ahead and apply the function f sub a to x and f sub a of y. And let's try this again by adding the two functions. And this time it works. So there might be an issue with my fun, but as you can see, I defined a new function which is a lambda expression, which would take a matrix, square the matrix and add 2 to it, and I passed x and I end up getting that matrix, and I passed y, I end up getting that. Now I could add or multiply those matrices separately. And once we have a lambda expression, we could actually create a regular expression, or a function, inline function. So r of x comma y equals f sub a of x, and let's do minus f sub a of y, and we could pass on values in, and r of 1 comma 3 ends up producing that result. So it doesn't know that x is going to be passed for f sub a of x, and y would be passed. The value, the variable lowercase x and lowercase y are being passed into f sub a of x and f sub a of y. So what we can do is we can try passing matrices. So let's define a new matrix Q and R matrix. and another matrix. And it still produces minus the symbolic expression. So the reason for that perhaps is because we did not define variables um, properly. So let's try u and v. Oh, we need a matrix. And matrix V. And R of u comma v. So what is happening here is what we saved in R is the matrix f sub a of x minus f sub a of y. So whatever f sub a of x returned and whatever f sub a of y returned after subtraction gets stored into R of x comma y as a full matrix, which is why we're unable to evaluate and get specific values for R. In the sense, we plug that in, we would still get the matrix because of the fact that f sub a of x minus f sub a of y is getting stored to R of x comma y. So there are other packages, just like we'd have packages in R, that we can import into Maxima. One of the linear algebra packages is Eigen, so we could do load Eigen, and by default the Eigen package comes with Maxima. So I'm going to do load Eigen, and you can pretty much see all the functions in load Eigen, and not only do we see the functions that are in the Eigen package, Maxima is also returning every single function that we created. For instance, we created R of x comma y, and it's showing up here. So we have matrices, for instance. It's not a good one. Let's kill Q and create a new matrix. And if you did not know, or if you do not know what the norm of a vector is, it simply is the dot product of each of the elements of the vector and summed over. So I have a matrix here. The norm in this case for that column vector and that column vector is not 1. However, we can convert a matrix to an orthonormal matrix, in the sense we would have a unit norm. So it is quite easy to do that. We can simply do unit vector of Q. Unit vector is actually a function in the Eigen package. Which oddly isn't giving me. what I would want. Let's try this that way. And there we go. So what we have here is a unit vector. In the sense, this column vector would actually have unit norm, and so would that. So it normalizes the vectors so that we end up getting unit norm. I could define a simple vector to show this. And that's what we'd end up getting. If we take the elements and find the norm here, we would end up getting unit norm. We can convert a matrix that has fractions, such as the previous one, to have fractions, decimals instead. So b float of w would end up giving a decimal value. We have seen b float before, and this is not something new. Inner product is a simple dot product, and we have a vector here already, and we'd end up getting that value. What is happening here is we are taking a row vector and multiplying by another row vector, and naturally it would do a transpose and give the dot product. If you don't know the dot product, A and B is simply A times the transpose of B. So we don't have to know what eigenvalues are, but if you're taking linear algebra, you should know what eigenvalues are. So eigenvalues satisfy the equation a minus lambda I for some lambda, or the determinant of a minus lambda I would equal to 0, where I is the identity matrix. So if we simply took a matrix, let's do matrix C, and it is going to produce those values. And what we see here, we could only have two eigenvalues because this is a 2 by 2 matrix. So eigenvalues are values of some lambda that satisfy this condition. The determinant of a minus lambda I is equal to 0. So the determinant of a minus lambda I would result in a polynomial of degree 2 for a 2 by 2 matrix. It would result in a polynomial of degree 3 for a 3 by 3 matrix, and so forth. Naturally, for a 2 by 2 matrix, we would have two eigenvalues. For a 3 by 3 matrix, we'd have three eigenvalues, and so forth. So this might seem quite confusing because we have one vector here and another vector there. So the first vector returned by eigenvalues would have the eigenvalues. So we have 2 minus square root of 17. That is the first eigenvalue, and square root of 17 plus 2 would be the second eigenvalue. And naturally, one might wonder, well, what is this 1 and 1? Since we're dealing with polynomials, a minus lambda I for a 2 by 2 matrix would be a polynomial of degree 2. Naturally, we would have roots that end up being repeating or distinct. In other words, there would be multiplicity. So here the two roots are unique, so the multiplicity is 1 and 1. However, if we have a repeating root, for instance 2 minus root 17 and 2 minus root 17 again, we would have a multiplicity of 2. So we have eigenvalues, then we have eigenvectors, and it's quite straightforward in Maxima. Eigenvectors of C would give us that, and you'd see a huge list that is being returned. So if we have a 2 by 2 matrix, the vectors are 2 by 1, and that's exactly what we have here. So in this huge list that we have, 2 minus square root of 17, square root of 17 plus 2 are the eigenvalues. 1, 1, those would be the multiplicity of the eigenvalue. So 2 minus root 17 has 1 root, and square root of 17 plus 2 has 1, in the sense the multiplicity is 1. And using these eigenvalues, we could find the eigenvectors, and those eigenvectors are saved in that particular list. So we have the first eigenvector here, and we have the second eigenvector there. So we can take the eigenvectors, and if we want to, we can normalize them using unit vector. We can convert it to decimal values using float and so forth. But keep in mind, we do have to do list operations here to get the right vector out. So as I mentioned, we could get unit eigenvectors. Instead of going for, or instead of finding the eigenvectors first, then normalizing it using the unit vector function, you have the flexibility to use unit eigenvectors directly. In which case, it is going to return the eigen values, the multiplicity, and the vectors. And this happens to be totally messy, so let us save that to P. And we could simply do a B float of P, and we end up getting decimal values. And there are matrices called similar matrices in linear algebra. If you had taken linear algebra, or if you plan on taking matrix analysis, similarity transforms, we say two matrices are similar if they satisfy this condition: U is equal to W times V transpose of W. I'm sorry, it's U times V times transpose of W. And if that is the case, then we say that U is similar to V. In other words, we simply call U and V as similar matrices. So if we want a similarity transform, we could simply do transform of C, and we end up getting the eigenvectors that we had earlier. So you may wonder why. Well, if we have a matrix and we have another matrix that has eigenvectors, then those two matrices are similar, and it gets into the entire concept of eigenvalue decomposition. So so a matrix and the eigenvalue matrix are similar to each other, which is why Maxima is returning the eigenvectors, because it is the simplest similarity transform that we can have. So there are other functions here, Graham-Schmidt, orthogonality, and eigenvectors in different forms. EA-vals is the same as eigenvalues over there, and conj of X is simply the conjugate matrix of a matrix X. So that would end functionalities with matrices in Maxima. In addition to typing matrices here, we could also go up to algebra and say generate matrix. We can specify the number of rows and number of columns and give it a name. We'll call it uppercase K, and over there we provide the elements and OK, and we end up getting that. And that seems quite messy. The reason being it is treating each of those as an element of the list, and so the entire list over here gets carried over for every single element. So if we want an actual matrix with the gen matrix function, we simply specify 1, 2, minus 1, 1, 1, 2, 2, 1, 1, and 3, 3, and that is giving us this mess, which it shouldn't. Let's try something else here. Two by three. Strange. Perhaps. Let's go back to generate matrix again. 9 and give it a name K. At most 5 arguments. When in doubt, we Google. Um, ah, we have to specify an array. So Gen matrix requires an array. So let's create a temporary array. Let's see, 1, 2, 3, 4, and fixed number. Well, must be a symbol or a list. Something is not right. Ah, so to create an array, we simply specify the variable name followed by its dimension. So A is an array now. Let's try 1, 1 and save 2. And A of 1, 1 is 2. And A of 2, 1 minus 2. A of 1, 2, 0. And A of 2, 2 is 8. So we end up having an array, and we can pass this array to Gen matrix and specify the dimension 2 by 2, and we can save it to K. And we end up getting that, which is 2, 0, negative 2, and 8. Similarly, we can generate a matrix from an expression or C plus D. So what it does is it creates a lambda function by default. It takes in values I and j, passes in to the lambda function, and then generates a matrix. So by default, the lambda function is going to return an array which can then be used. So the enter matrix part, you can have create a diagonal matrix, a symmetric matrix, and so forth. I am going to call this E, and it puts in diagonal elements by default and blocks out every other value. So we end up getting a diagonal matrix. As you can see, each of these functions would end up calling the built-in functions that we discussed earlier today. So For instance, if we went to eigenvalues and eigenvectors, it is automatically going to go and look for the function eigenvectors or eigenvalues. So there is one other thing, the characteristic polynomial, and that is something I'd mentioned over here, the determinant of a minus lambda I. So if we have some matrix, for instance C, we created that already. So when we try to find a characteristic polynomial, we simply have to type char poly and C, and it's going to give us an error. As you can see, we need to pass the matrix and a variable for that part right here. A commonly used notation is lambda, but you can use, other letters. For instance, I could say the variable is going to be, let's do beta. And we'd end up guessing that, and that is the characteristic polynomial. And if we solve this, we would end up getting the eigenvalues that we had earlier today. So we could go for equations, or we could go to one of these, for instance, roots of the polynomial, and by default I'm taking the previous roots, the previous polynomial, so all roots of that equation, 1 minus beta times 3 minus beta minus 16, we end up getting those values, and these values are the exact same ones we had somewhere earlier today, right here. So, and that's what we end up getting. So there are multiple functions that we can utilize to apply on matrices in Maxima. So we just went over a few things, and things that you need to know are the eigenvectors and characteristic polynomial and so forth. The theory behind it is something that I cannot cover here, but all you have to know here is how to use Maxima to do matrix operations, trivial ones and important ones such as eigenvalues and so forth.